Hello folks, I'm back with the sequel now to the chat server and Erlang demonstration video that I did previously, where we use ZX to create a very simple Telnet chat server. Now, of course, there was a tremendous amount of cheating involved in the actual coding of that one because the default template project that ZX produces for you is a Telnet Echo server. The example that we're doing today we did a little bit of editing with that, right? We added like some places where you would put commands and things to demonstrate that could work. But we didn't really go anywhere with it. Today what we're going to do is implement chat channels so that it can work more like an IRC service. So if you join a channel, it'll create, if you join a channel that doesn't exist, it will create that channel on the fly. Once everybody leaves the channel, that channel goes away. And there's the beginning really of a permissions system in this where the chat channel has an owner, and until the owner leaves that channel, he's the owner. And once they do leave the channel, the owner is nobody, and anybody can claim that title for themselves if they're just the first one to do it. The owner only has one authority, and that's to set the topic of the channel. Well, that's not a very in-depth, authorization system or security access system or whatever. But we'll look at the code and you'll see that just the fact that you've got an owner is kind of the beginning. That's the gateway to implementing more interesting commands like kick or ban or kline or silence or whatever. In addition, you can implement, access lists or different permission levels, users with different roles. So you could create list roles within the channel state, and the channel could know who's allowed to do, take various actions in a channel, who's authorized. And the owner could be in charge of adding them or whatever. It's very obvious to see how you would implement these things. It's so obvious that implementing a new command only takes like a few minutes. This whole adding channels only took about 2.5 hours. It really took 2 hours, and then I forgot to do topics and owners and stuff. So I just did that now. I wrote the channel stuff yesterday, but it was getting too late to do a video on it. So I came back today and noticed that I didn't put the topics in like I wanted to, because I wanted to show an example of having notifications that something changed if you're in the channel. So anyway, before we look at the Trash Talk server code itself, let's back up and just really quick look at the templater for the service worker pattern and what that even means, what the service worker pattern even is. So we're going to create an example project here. It's going to be just like the Telnet server that we did. I don't care about names here. We'll just call this foo. Everything's foo today. F is fine. My name is foo. I'm foo at foo.com. Right? It doesn't matter. The description is foo. Don't have any of that. Okay. So, when we're in foo, we know that we can do, because we just created this thing, which is kind of the sloppy Telnet Echo service, right? What we're going to look at here is the application foo has one subservice, clients. And clients is actually, this process is a named process, and it is a supervisor. It's the top level supervisor. There's a manager, client manager, just as we discussed previously, and there is a worker supervisor. Now you notice that there is no listener yet because we haven't told it to listen, and this is the vanilla thing that just got spit out by default. So in the startup, it does not define that it should listen on a given port. So we're going to give it that command in a second. We'll see what happens. This is, if you're not already familiar, with some of the built-in Erlang tooling. This is called Observer, and that's, I should explain this, I suppose. Observer is a runtime inspection tool that comes with Erlang, and if you have WX, if you're on a GUI system and you have WX, built on your system, then it can show, you can build GUIs with Erlang, which is what we were doing in previous videos, right? With the, if I had selected up here, build a GUI application with ZX, it would have been making a WX GUI application. This is one of the built-in GUI applications for Erlang, and it shows us what's going on with the system. We can inspect the runtime and see in detail what all's going on, to the point that we can see what Erlang applications have been started up inside the runtime. So this is our top level supervisor for the application. This is the one subservice that we have. Let me make this a little different aspect so we can watch things change live. This is a worker supervisor, and this is the manager. So pretty much any time that we talk to the clients, we're going to talk to the client manager, right? So let's do foo listen and see what happens. Okay, the supervisor has created a listener. If I connect, we'll see another one pop up. And that's because this first one here is now the connection handler, this guy, right? And it'll go away now because it's retiring. So, and this is listening for a new connection. So the first connection spawns, a listener spawns its successor on connect, right? Just as we discussed the other day. And if we go back and do foo ignore, we'll see that that listener goes away because he's ignoring everything now. So now we'll halt the system, and I'm going to go into source, and in the current directory, if I do ZX template SWP, that's service worker pattern, it's going to ask me what's the name of the service. So let's say that I wanted to create channels. I'm abbreviating it to Chan. I could call it channels, doesn't matter. Service name, channels. And this happens. Now, I had these modules previously, but these just popped up. Now, you notice that client manager, client supervisor, and client's service name, channel manager, channel supervisor, channels as a service name. Now, the channels are, these are just like empty templates of how to, like, this is a gen server, this is a gen server. The relationship they have to one another right now is really just that they're part of the same supervision structure. It's up to you to write all the behavior in that you want, but it's all templated for you, and that removes a lot of the kind of annoyance of creating a new service. But this guy right here, our top level supervisor, is not aware of that yet. So we're going to add it to the supervision tree, and I'm going to cheat by, I'm just going to copy paste. So channels, and okay, so we've got a new child entry. We know it's a supervisor. It's the top level thing. So this whole structure is now clipped in. That's all there is to it. So if I do ZXH, run local again, and this time, whoa, start. All right, now let's look at the applications running. We've got our application supervisor. We've got a client's service, just like we had before, and we have a running but blank, right? These are like pretty much empty. You don't ever really have to change this guy much. But anyway, we've got an empty service structure here. We have a top level supervisor that has 2 children, the channel manager and the channel supervisor, and below that, if we create channels, will pop up here. Now, the reason I'm showing you this here is this is exactly the same way that I made the initial template code for the channels that we're about to walk through the code on in the actual, I'm silly, in the actual trash talk application. So let's go over here, and I'm going to open another 2 windows. Let's get these so we can read them. And whoop. All right. So we see here, trash talk is abbreviated to TT as a prefix. TT clients, as we know from the previous video, we've already put the listen instruction at the end of startup. So this is already listening on its own. So we have a listener listening on a socket, and we have the channels thing. I abbreviated to chans, but it doesn't matter. This is the exact same thing that you saw just a second ago, except of course these are populated with code, and the other ones, were not. So let's give it a little spin here. If I do telnet localhost and so we're seeing connectors open up, right? So client handlers are opening. What should I call myself? So this guy's going to be Jerry, and this guy's going to be Gene. So if there's a couple of commands built in here, and I'll just show them real quick, and then we'll see how they're implemented. No channels exist yet. So if I do join, let's talk about space stuff. Join space. Okay, let's add a topic to space. All about space. Now, if I list it, or if this guy lists it, it's done, right? Now, if this guy joins space, by the way, we see space here now, right? Something you can do with this tool that's pretty neat is while something's running, you can open up process info, and you can actually check its state. This is the internal state record of that process while it's running right now. And so join space, Jerry joins space. Now if Jerry tries to other things about space, set the topic, he doesn't own the channel, so it says no. And if this guy leaves, and this guy claims space, my channel now. So we can see that. Now we also still remember the original code had that global chat thing where anything you wrote would go to everybody. We still actually have that, and it's called a shout. So message to everyone. Okay, so that is going to show up everywhere. Since Gene is not in space, we can get into space, and Gene blah blah. So this is like a primitive interface to essentially an IRC type system. It just doesn't have all the permissions stuff implemented yet. But as I said, that stuff's actually pretty easy to do. So we're not going to it's easy to do, like each different thing is easy to do, but it's a lot of things to do. So I'm not going to spend much time on this because we're not really going to pursue this example. Like I don't think anyone's interested in me setting up a chat server for people to connect over Telnet right now. So let's just look at how these are implemented. And unfortunately, I haven't made a help screen because that's just not really the thing to do. Also, the previous by, if you just do by or like anything, it'll just give you that. So, and if you do a bad command, it'll just question your sanity. By has become a slash command. So in this paradigm, slashes are command prefixes, exclamation marks are shouts that are global messages to everybody, and any message that's prefixed with the hash mark and then a channel name will, well, actually we're in space specifically, so green beans will go to everyone in that channel except for the original sender, because we're going to not send that to everyone, but a shout will. Blah, blah. A shout will go to everybody, including the sender. So that's just how this works. And we can see down here at the bottom, we've got one channel supervisor. We've got one listener open, one connection still going. We can, add that. Oh yeah, also Gene, right? That username is unavailable. Because Gene's still connected, so we've put a couple little protections in here for sanity, but there's not like a whole lot of checking in this system. If we make another one, let's make an Erlang channel. We'll see our Erlang channel pop up there, right? So this is all as we retire. The Erlang channel now has nobody in it, so it's going to exit. And the same thing will happen here, and we're back just down to one listener. So let's look at how all that stuff actually works, because it's fun. So once again, this is our application module. That's the app mod is the thing that kicks it all off, and this is defined as the application behavior, as we discussed in the previous video. The client handlers still all work almost the same way, with the main exception being code has changed in client. And this is a good place to start because it's the entry for where the commands come from. If we look over here, what happened when I connected? Telnet connect. We got a welcome message. We didn't get that before. It asks what's your username. It won't let you duplicate an existing username. And then we're into command interpretation line by line. The way that works in here, the state record has expanded a little bit. As I said in the previous video, I like to arrange things so that we can check the interface functions, the state structure, and then wherever the main receive loop is, so we can get some sense for what this process does. So this guy has to start with a socket so he can listen. Starts as successor, as we know from before, so the socket's kept in state. The user's name is kept here so that it's known. And then we have a list of channels to which the guy belongs. And that's, of course, dependent on having channels exist at all. Channels are records. They each have a name, a PID, and a monitor. And the reason for that is we need to monitor these channels. If they crash, we need to make sure that we clean up our channel list so we don't have phantom channels sitting in here stale. So we will expect to find a handle, a receive that matches on a down message somewhere later. The reason that I used a list of records is because we're not going to have tens of thousands of these. You're not going to be enrolled at tens of thousands of channels, chat channels at the same time. So we don't have a performance issue with traversing the list to find a match. So if we're looking for a channel by PID, like, let me back up. If we use a an indexed structure of any type, doesn't matter what it is, whether it's an ETS table or if it's a map or a dict or whatever, any kind of indexed data structure, we have to pick what's a key. Well, we have two really strong candidates, possibly three: name and PID. We might be searching for a channel by name, or we might be searching for a channel by PID. Do I really want to have two maps? One that is indexed over PIDs and one that's indexed over name? Or do I really want to have a much more complex system where I've got everything is a single map indexed by name, but then the couple of times I do need to search by PID, I've got to dump that back out to a list and then search as a list anyway, with the added overhead of dumping that map out as a list. It's, there's not, because we don't have a performance issue and we haven't identified a performance issue and we're trying to figure out how to get the code structured in the first place, lists of records is a really good, simple to read structure. And it's also really easy to understand when you see a state dump of like what's in state. So maps can often be easy to understand in dumps also, but this is a very simple way to start out. And again, people will say, but performance isn't everything, especially when you're dealing with human speed reactions. This simple little chat system could handle tens of thousands of concurrent users all chatting away at once, and it really wouldn't have much overhead. We could run it on a pretty slim system. If you put it on raw hardware instead of a VM, you can really do a lot. Anyway, this is our data structure. We see some interface functions, right? But we know that the socket communication is not going to come in as a function. They're going to come in directly as messages. So the commands that the user issues don't show up here because we're interpreting the commands directly in the client handler, which holds the socket. If we were to want to have a web interface, a desktop application interface with its own protocol, and a Telnet interface, well, then we would want different kinds of client handlers, and those would talk to another process that represents the user. So then you could actually have multiple login, right? That's how multiple login works, is you have multiple connection handlers, and the user is, the client itself is represented, I guess, the client connection is separated from the idea of the user. And the user is a process that stood up if there are any number of connections that are live for that user. So they can all communicate with the user itself as a process. So in that case, we would have interface functions for user commands, because somebody might be clicking a button to send a chat message. Somebody might be typing in a chat command, and somebody might be selecting a chat command in a different way somewhere else, like from a web request or whatever. So the service interface, chat, so it's going to send. Remember, this is a pure process, so we're not using Gen Server here. We are using ProcLib, but we're not using a Gen Server here. Chat is going to send the client, which should be a PID, a tuple, a message that's this tuple, chat, the channel name, the sender, and the message. And then, obviously, that's going to cause this process to format that in a pleasant way and send it across the socket to the client. Notice. So this would be for notifications that are not chat messages. So like the message that Jerry has entered the channel, Jerry left the channel, Jerry changed the topic to whatever. Those come across as notices. So notice from what channel and what's the message. And then shout. That's the system-wide blast out to all clients. Will be in a shout. And then, okay, this is our startup stuff that, we already went over this stuff. Okay, now remember we had a greeting, get the name, then move into the main loop, right? We weren't really into chat yet. So the way that we did that was as soon as we accept a connection, we get the socket, we start the successor immediately, exactly the same as before. We're going to go ahead and print out, just standard out still. We could log this, or maybe we don't. Maybe we just get rid of this because we don't care. We log the connection, set the socket in a state, and we greet. But you notice that we have not yet enrolled with the client manager. It used to be notify and then enroll immediately, right? So we'd start up the successor and then enroll. Here we're not doing that. First we go to greet, and greet is really simple. We have a function called forward, and it looks like forward accepts the socket and something to send. And that's really all it does. It calls gentcp send. We'll look at it in a second. Really, the whole function of forward is to add the line terminator to this, so that we're not typing rn all the time or forgetting to do something like that, because that's just a trivial frustration that you can forget to do, and then your formatting looks weird on the client side. So I've just abstracted that step out behind a function called forward. So this is just gentcp send. Socket and a message. So we're going to send a welcome string. This could be ASCII art or anything. Sky's the limit with whatever you want to do in terms of like text graphics or colorization or whatever. We're not doing any of that here, but you can definitely mess with it if you want to change things up. Prompt the socket. If we get, so we're asking what's your username? We're going to prompt the socket, which, we'll check the prompt function. It just sends out that little, the little whatever, greater than sign as a prompt, and just leaves the cursor there with no line terminator. If we get back nothing, an empty string, it'll, send them a snarky message, and then we will loop back up to greet to try it again. If we get an actual name, we'll try to enroll. Now enroll, so we have a locally defined enroll, and we still have the client manager enroll. Client manager enroll used to just be return OK, right? No matter what. Now it doesn't. Client manager's become a little bit more complex because it needs to check if that name exists or not. So it has a registry of names, and it's going to check to see if that client exists or not. And it's going to give us an OK message or an error name taken. If the name is taken, we're going to send that error message and go back up to greet, right? And so we're just going to keep going through this until the user picks a name that doesn't exist yet. Once he does have a name that's acceptable, we'll go down to loop, and loop is defined almost the same way as it was previously. This is where we see our receivers, our handlers for the chat, notice, and shout messages, along with just getting a socket message. So we had defined the dispatch function previously. Instead of trying to match on every single possible command right here, we're going to defer that work to a dispatch function so that we're not rewriting new state, loop, parent debug, new state constantly, right? We just want to send the message in the state to the dispatch function, and dispatch will send a new state, and we'll just loop from there. So we're going to keep this a little bit tight. So dispatch string chomp, all that does is remove the line terminator. We're in line mode right now, so Erlang, the runtime, will not send us a message until it gets to the carriage return. But we're chomping the messages to get rid of those, because it's having trailing line endings floating around the system can become a little bit frustrating to handle. So we're handling it in one spot right here. Chat message, it formats the chat message and then forwards it. Notice, it formats the notice message and forwards it. Shout, it formats the shout message and forwards it. Like, these are really simple to understand. That's the whole thing. They're just defined right here in line. All they do is forward a message down, through the socket, formatted in a whatever way is appropriate. Channel related messages always have the hash. Shouts always have an exclamation mark. So, and then, the other as a user, the other prefix that you see is a slash for commands, right? But those don't ever get echoed back. So let's check out the dispatch function. Oh, one more thing that we've got. Remember, we've got monitors. We are handling a down message here, and we have a handle down function. And this handle down function works almost exactly like the handle down function in the client manager. We'll find the handle down function, some form of it will appear in pretty much any process that monitors another process will have a handle down. It's like a just in case. It's a reaction. How should I react to a process I'm depending on failing and crashing? That's what handle down is for. This is not a standard function. It's not like an OTP function per se, but this thing occurs so much that you're going to be writing handle down a lot because process A expects process B to be alive. And, you know, it's common to have, this is a pretty common thing to write. The reactions, the things that you write inside of handle down depend on the way that you're managing the data inside of your state record, or whatever state data that you've got. Because like this could be an ETS table, right? So it might not even be in a state record. It could be this different thing. How your data is structured, and what data relates to what data, and so on. The body of handle down, there's no generic way to do it, because the reactions that you may wish to take, the action you may wish to take on receipt of a handle down message could be completely different. And you may only have like a fixed number of processes that you're handling, and they could be of a unique type. When that's the case, you don't even have a handle down. You match directly on different types of monitor reference or PID or whatever that is held in a state record in a special way. So you might not even have a handle down, even if you are monitoring something, if you're only monitoring one or two unique things in a specific way. So that's that. This is the prompt thing that we saw up there. In the code, I really could have moved this up closer to that. I wasn't sure if I was going to use prompt a lot or not. So I just wrote it and then left it there. And all prompt does is, this is like a default prompt. We could call prompt with, specialized text. I wrote this as a function here because you'll see this a lot when you're doing like text service stuff like this. You're going to very often want to provide a prompt of some type, and it's easier to do it in one spot, especially because it involves a receive. Remember we talked about active once in the last video. You've got to call this if you're waiting for socket traffic. And also note that all these other messages up here, we're not waiting for them. They're going to stay in the mailbox. So as soon as we go back to loop again, we'll be able to pull those out. But here we're doing a selective receive just on whatever the socket sends back, or if the socket closes. And if the socket closes, we're just, we're out. We're done. So that's this. So dispatch, this is what we're looking for. So if dispatch sees a hash first, that means the user's trying to send a chat message to a channel. So we're going to split the channel name, which should be separated by a space from the rest of the message. We're going to break that off from the message. So that's going to consume the channel name, and it's going to consume one space off the end of it. And then the message will be intact behind that. If we get this form, then this is legitimate. This is the shape that we're expecting, a channel name with a message, and we're going to call the chat function channel name, message, and state. Now note, this chat's not the same one as the one up above. This is chat 3. If we don't get that shape, if we get any other shape, if we get, for example, if the user had just sent in a hash and that's it, well, that's not a command. It's just like a typo. If they had sent in a hash and a space and then a name, that doesn't really fit either. If they sent in just a channel name but no message, we can't handle that either. So we don't care which shape this is. If we want to provide really, really detailed error output to the user, we might match on each different case because they will be shaped differently. We could have an empty list, a list with a single, just a channel name in it, and so on. But we don't care here. We're just going to call a derp function. Derp is our, the user derped. He did something that you can't do. So we're just going to send him back a generic response, which is like, what? That's I think the message that it actually sends back is the, argle, blargle, glop, glyph. That's just an old thing that comes from a mud whenever you make a typo like that. So I'm just kind of using that here. But if you wanted to send a help message back or a really specific error message, you could do that. Or you could capture the whole string up here and send it back to him and say, hey, this doesn't mean anything. You could pick it apart and get as detailed as you want. Here, we just don't care because it's like a trivial chat system. If we receive this, the exclamation mark, that's our shout, and we know that's a shout. So the thing that we do with a shout message is we send it to the client manager, just like we did previously. The original code that was templated by ZX for us, that's like every message was a shout, right? It just forwarded the same message to everybody on the system. And that's still what this does. We've just kind of, instead of calling an echo, we call it shout. And the way the client manager does it now is instead of sending a raw message down to a naked Erlang message down to all the clients, now it calls the shout function on all the clients. And then we return the state. So we're always returning state. All these have to return state, right? Because if state is updated by one of these commands, then we have to return the new state. So all these have to return state. Slash, the command prefix. And when you're trying to figure out how should I write my help file, sometimes it's helpful to just clip these out and sort of delete everything after it and start explaining them and make that your help screen. So list, we've got a list function. Users, we have a users function. Join, we have a join function. Leave, we have a leave function. Help, we have two help functions because there's two shapes that help might take. Note that we've done string split again, right? So we could have a following thing, or we could just have help by itself. Sometimes it's also good to just clip this out and have one that's just H, or a question mark or whatever. We could, for example, common users coming to a system for the first time don't have any idea what help commands are. But there's a couple of common tropes, right? Slash help is one of them. Slash H is one of them, and slash question mark is one of them. So we can redirect all these to help. In addition to that, we can do as much as you want. You can make help. You can make a help too, where each different help looks up a clause, like to give helps for a specific command. Like if you did help join, help leave, help users, and so on. So again, I didn't implement all that here, but I'm showing the purpose of this is to show you where you would where that process starts and how it looks in the code, so that your eyes can kind of adjust and see, oh, that's where that lives. People who hate the Erlang case statement, this is the moment when you stop hating the case statement. Also the moment when you stop disliking matching, because this is much easier to do here, much more straightforward to read months later, especially, than a lot of other places. And if we get a message that has no meaning to us, it's not prefixed with anything appropriate, we're not going to broadcast those to everybody anymore, right? That's become a specific thing, which is the shout command. So if you just send in a bunch of junk to the server, it'll just ask you if you're talking to yourself because it's not going anywhere. So chat, let's see. Let's not look at chat yet. Let's look at join, because join is an interesting one. The join command, where that is it's just straight down below this. I'm jumping. Somebody mentioned I jump too much when I do these slash search commands inside Vim, but actually let me also... there we go. Let me give you some line numbers so you can help. So this is easier to navigate if you're not familiar. I'm going to wrap all this up and put it in a repository so you can cruise through this code at your leisure. And these line numbers may help you find stuff. So join, then we expect a hash. It's a rule in the system that every channel name has to have a hash. So we're going to clip it off there and just get the name itself. Join a channel. We're looking chans. Remember the chans list up there? We're going to check if channel is a member of chans already or not. If it's not, then we're going to call the channel manager and ask to join it. And then we're going to get the channel PID. We're going to monitor that channel in case it crashes. We don't want to crash because it crashed, or we don't want to do anything silly because it crashed. Like try to send it messages continuously if it's not alive. We're going to create a new channel record with that information, the PID, the name, PID, and the monitor. And then we're going to forward to the socket that you, the user, successfully joined that channel. If you're already in that, then we're returning the updated state, right? If this channel is already a member of channels, of the channels that you've got, if that's true, you're already in that channel, you shouldn't join it twice. And we don't want to have the machinery have to check deeper down. We're just going to cut this off right here because this process knows what channels it belongs to. So it's going to return a message, hey, you can't join that yet. And if you did anything silly, we're going to just derp back at you. So how does this work? This is the interesting part. We're getting a channel PID back, and we're expecting that this is always going to work. If it doesn't work, we want to blow up because it should be a critical failure. We're going to open the channel manager, and it might be good actually to let's open Observer, and we'll actually just look at what's calling what. So this is a client, one of these guys, is going to call the channel manager. The way he knows how to call him is because the channel manager is a named process, so we don't have to do anything. We don't have to like look up his PID or anything. And we're going to call join. So let's get over to channel manager, and we're going to look up. We'll look at join. Just real quick before we do that, just like any other process that we're going to look at, what's this thing manage? It manages channels. Well, what kind of, and that's all it's got in its state record is a list of channels. Okay, well, what defines a channel? A name, a topic, a PID, and a monitor. Well, that's very managery kind of stuff. It's got a join function, a list function, a users function, and a topic function. So let's see what they do. Join is the one we were curious about, right? That guy, the client, is sending join, channel name, and username. That is translated to a message. Remember, this is being called in the client's context. So when this process calls this function, it's defined on this module, but this call is in the context, execution context of the client still. So when we call self right here, we're going to get the process ID of the client to include in this message. So this is sending a synchronous message to the channel manager of this form. It's just sending this tuple, join, channel name, username, join what, who, and then more than just who, which process ID is that also? Because we want to know. Because if we just have the username, we would have to do another lookup inside like the client manager to look this up. We can just nail all this right now because the channel is going to want to maintain a list of its subscribers, right, of its membership. And if the client process crashes, which is the most likely thing to crash in a system like this, it wants to, remove that guy from its list. The same way that the client wants to remove a dead channel from its list. So we need to give the PID to it. So join channel name, username, initiates this message. That's handle call. Again, I'm jumping, but this is just the gen server. This is that the middle, that handle blah section of the code of the gen server that's right in the middle. And it's the same idiom that we saw before. We get a message, join, we call do join, and depending on the nature of that function, we may or may not be sending a result, and we may or may not be updating the state. So do join. Let's go down to do join. So I'm just going to jump down to it here. So this is the tail end of that middle kind of gen server boilerplate section that's always the same. Doer functions, do join, channel name, username, and the user PID that we had, when we called self up there above, showing up here, and we've got a list of channels. Now, list key find. Remember, we're doing a list of records, so we can search by PID or we can search by name. In this case, we're going to search by name. So search the channels by name. If we find it, we're going to get that record out, and we're going to get the PID. Then all we have to do is tell that channel, let this guy join, username and the user PID. He wants to join you. That's a cast. We don't care what the return is, right? So it's just okay. It's an asynchronous cast. Then we're going to send a return result back to the caller, the client that asked for this. This is where that OK channel PID comes from. And then we're not updating the state because it's the same thing. But if that channel doesn't exist, we need to create it. So we're going to call channel start with the channel name, username, and the user PID, because he's the owner, right? So at startup time, that channel needs to know who its owner is, so it can just already be assigned. The return value of that is the OK channel PID, and we're assigning that to result all in one line here. We're picking it apart so we can get the PID because we need to monitor it also, right? The manager needs to monitor it. So it's assigning a monitor here, packing its record up for what it is. Remember, there is a topic element to this, but it's an empty string right now by default. So we're just sticking with that. We create the channel record. We're sending this result, right? We're sending this result back, which is the same form of result that we sent in the previous one. So either way, this is the return result, and state is going to be updated to add this channel to the channel list. And that's it. That's how you do the join thing. So you've got this check if it's alive. If it is, send the PID back. If it's not alive, spawn it, monitor it, then send the PID back. And the client receives the same reaction either way. So that's how we get our join command. We're going to join a channel. That's how it works. So how about a chat? A chat message, which we discussed here. I'm just going to hop down to chat, which is, okay, it's not far. Chat, you notice all these functions are really, really short. That's easier to kind of understand than doing these big, long, it's easy to keep this tiny amount of code in your head. You'll notice that there's a case that's assigned out to OK. That's because both of these return OK. And I'm returning state unchanged regardless. So I've just done this a single time. You'll see a different style sometimes where people will match the OK right here and put return state in line, and they'll just have it in twice. It doesn't really matter which way you do it. This is kind of an idiom that I use, and this is a style that I use for a couple of different reasons. One of them is so that we don't always throw away case result returns, because one of these could actually have a mistake. One of these could have a fault, And if it has a fault, we want to blow up on OK, because it's not, we're asserting OK with this equals here. Because in Erlang, remember, the equal sign is assignment, matching, and assertion kind of all in one. So we're asserting that both of these operations, the chat operation and the forward operation, would have both succeeded if they needed to. So in whichever case. So we're going to send a chat message to a channel. Now we don't want to have a user that's not part of a channel, that's not a member of a channel, just blasting messages off to random channels. So we're going to keep things in scope a little bit better within the chat world by checking, is that channel in your subscribed channel list? And we don't have to check with that channel. We can just do it right here in this process because we already know based on how join worked, right? We already added that with the join command. If we do, then we got its PID. We're going to send the channel a chat message. If it's not in our channel list, it's going to say, hey, you're not in that channel. You can't send it a message. So let's check out the chat. Oop, that was the channel manager. I want the channel itself. So same thing here. First time we're looking at this module, this is the channel worker. We're going to check really quick what the state looks like in here. So we've got a state record. The channel has a name and it knows its name. It's got a topic and it knows its topic. It's got an owner, maybe, and it's got users. A user is defined as a name, a username, a PID, and a monitor. So we've got client interface, which is kind of easy to see up here. Join. These are the things clients can do. Join. Users is listing users. Send a chat message. Leave the channel. Set the topic. So topic 2 is this channel PID plus a new topic string. And topic 1 is to retrieve the topic. What is the topic on that channel? And claim ownership of the channel. So we'll look at topic just to see how, well, we'll look at topic 2. We'll look at the assignment of a topic to try to understand how permissions can be written in a way that's a little bit more like short and concise and gives you a lot of opportunities for checking. Checking like little chunks of your code instead of having one giant function that has to evaluate user input, as crazy as user input can be. So it's better to chop things up. We'll look at that in a second. Anyway, right now we're looking at chat. So we saw that the client checks if it belongs to that channel or not. If it does, it's going to send a message over here. A chat message is the channel PID, the sender, and the message. So the sender is a username, right? And I'm doing strings here. You can do this in binaries. It doesn't matter. Everything's an IO list anyway. I'll point that out when we go back into the client module. We'll look at how that makes like messing with strings kind of easy on this side. So chat is a gen server cast. So this is an asynchronous message, and it's going to send a message of this form. And that results as expected. I think at this point you probably are picking up a pattern that the chat interface function sends a chat message that initiates a call to do chat, and then we return the state because that's how gen servers work. And you know, it's boring. That's good because it's easy to understand what's going on. So do chat, sender name, message, sender PID. These are the arguments that we just saw before. Well, send. So we're building a send function. Why would we build a send function in line right here? The reason, and this is the number one reason that you actually use lambdas in Erlang. You may have seen my previous video that I made about how to build, you know, object-oriented, like OOP style objects using Erlang. and of course it leans heavily on closures. Erlang is a functional language, but the use of closures to represent interactive objects, even to the degree that that happens in Scheme or Common Lisp, is not very common in Erlang. And the reason is we just don't get much out of it. And having long-lived lambdas floating around the system, or long-lived closures floating around the system, is not as useful as it could be in most cases. Sometimes it's a big win, but that's kind of few and far between. The most common case that we have for using closures in Erlang is stuff just like this, where what we want to do is curry out all of the arguments from a function to where there's just one argument that we're going to pass in. Because if we do that, we can use all the cool list operations, all the standard functional list operations, for each fold. Fold takes 2 arguments, but we're going to curry out all the built-up state that we're going to depend on, that this function needs to be able to access. We're going to close over it inside of the anonymous function's scope, give it a name, and then pass it into a list function. So we can pick what the arity is. And if we look up the lists documentation, the lists module documentation, we can see what arity function we need to build to pass in there. Sometimes you'll have independent functions, like you don't have any new state that you got to pass in. So you could just have an independent function. But in this case, we do need a closure. The reason we need a closure is right here. We're going to be iterating. We want to send a message to all the users, right? So in the case, we're going to open up the user record and get the PID out because we have to send it a message. Well, actually, in this case, we're going to call an interface function on its module definition, and that will initiate a message, right? From inside of this module, we don't really care how it's implemented. So we just need the PID. So if the PID is the same as a sender PID, then we don't want to forward the message to them. So if it's the same as the sender PID, then we're just going to return OK from this. So it's not going to take any action. If it is not the same as the sender PID, then we're going to call client chat, which we saw earlier, right? Chat gets these arguments, it makes a chat message, and it sends that. It uses the exclamation mark operator, the send operator, to send the message directly to the client process, right? So it calls this interface function on the TT client, on the trash talk client, and that's it. So we check the PID. If it's the same, don't send a message. If it's different, send a message. And that's it. That's what send is. So we needed to close over this state, needed to close over this state, needed to close over sender name, and we needed to close over the message. So these are all things that are inside the closure. The PID is the only new thing that we get each iteration. Now that function is now got a name, send, and we're just going to plop it in here. Lists for each send users. What for each does, it just returns OK, and you call lists for each if you only want to get a side effect. Like you want to commit some, action that is not like a data update. Any kind of side effect that you want to do over a whole bunch of things in a list is what for each is for. So that's it. This just blasts off. If you have 100 users in that channel, this will just call send 100 times. Once for each user, returns OK, and then now the channel is just waiting again. So the channel is a broadcaster whenever you call chat. So let's go back and look at the join. Remember, this is our command list, right? Join is a little bit more complex. I'm sorry. We already did join. Let's do topic. Topic is an interesting one because it kind of initiates quite a few actions. It's a simple thing, right? Having a topic, but doing a topic right and having it be a protected action is the important thing. The way that topic is implemented is very, very similar to the way that you would also implement ban, kick, silence, any of these other, voice, any of the admin type commands, because topic is an admin command here. So let's go look at topic. The first thing we'll notice right away is there's topic, then topic 2, then topic 3. This is all one idea, right? Setting the topic is all one concept, but each one of these has a case. So just the structure of this code, we've got a case that may result in a call to topic 2. We have a case that may result in a call to topic 3. And we have a case that may result in a call to the channel topic function being called. So what are these cases? If we get a channel name separated by a topic, and then space separator, and then a topic string that we want to set the topic to, then we're going to call down to topic 2. If we only get a channel name though, then we want to call show topic, because remember we had topic 1 defined as show me the topic from the channel, and we had topic 2 defined. The 2 arity is the setter, and that's a pretty common. If you write an interface module, it's pretty common to see like the setter is some name 2, and then the getter is some name 1, instead of being set thingy get thingy set thingy get thingy. A shorthand for that is just thingy 2 is the setter and thingy 1, like whatever the thing might be. In this case, it's a topic. So topic 2 is a setter. Topic 1 is the getter. Is a fairly common idiom that you'll see in some code. Not every shop does it that way, but there's a lot of places. Maybe that's a thing out here where I work most often. But that's a pretty common pattern, is to see, topic 2 would be a setter and topic 1 would be a getter. And you just check down, and you need to read the code to really understand it, or read the docs for it, and it'll tell you. Anyway, so this is 1 and 2. So we're going to continue with setting the topic. If we just get 1, we're going to show the topic. And if we get something ridiculous, then we're just going to derp at the user. Notice again, all these have to return state. So we do have to carry state through. The reason is all these need access to the socket, and they have to return state anyway. So topic 2, we've got the channel name, the topic we want to set, and then now we're going to look in the state. So we're going to find, am I a user? Am I in this channel already? If I'm not, then of course I'm not going to even try to send a message off to change the topic. We're not even going to bother the channel process. If we are in this channel, topic 3 basically swaps out the channel name for the PID, because that's what matters. So topic 3, channel PID, topic state. We had channel name, topic state. We found the PID, so we're just switching that out. Now you might look at this and say, why don't you just nest these cases? Well, if you nest those cases, you get that like really crazy, you get mountain climbing code, and it's hard to read. And the way that case is written syntactically, the ends kind of clip in, and it just gets really weird, and you have double and triple at the indentation going way, way out. And it's hard to read. Readability is only one issue though. The other issue is that because we have separately defined function names, I don't have, if I'm writing tests or if I want to play with this code in the shell, which I very often do in development, want to play in the shell to see how something acts, I'll export all the functions from a module, and I can cut to the chase. I can call topic 3 directly and not worry about this stuff to see what actually happens. So you get more entry points. And if you're writing tests, it's a lot easier to write a test with a very tight case just for topic 3 than it is to write if this is all in one big blob, right? Same thing, like imagine if we rolled all this back up, we could write all this code inside the receive clause in loop. We don't need any of these functions. We could write one gigantic loop function and not break any of this functionality out at all. And it would be a big, long, nasty mess, and you wouldn't be able to find anything very easily. And you could never call one segment of code and just test that one segment of code. Notice, there is no global state here. We have no visibility on global state. We don't have a concept of global state. Everything is in the argument list, which means that you can test just topic 2 by itself or just topic 3 by itself. And you can do that iteratively, which means you can write much more interesting tests to the extent that tests are even really useful to write at all. At the same time that tests become easier to write and you have more entry points, the code becomes so much easier to understand that the need for extensive testing all over the place is somewhat reduced. So you get two effects from breaking things out like this. So some people are surprised. They're like, wow, you have topic 1 and topic 2. There's only a single clause in each one. Why would you do that? This is why. To give myself more entry points and to make each clause of topic very, very stupidly easy to understand. Even for a beginning Erlanger, this is easy to read. Even for someone who doesn't know Erlang, once their eyes kind of adjust, this is not hard to understand. We're doing one thing, checking one case, like a really simple return condition, right? That's what we want. So, topic 2, channel name. Topic 3 is basically the same call with the PID swapped out for the name because we found it because we're in that channel. Now we're going to call the channel itself and say, hey, change the topic. So we have to know the PID, which we got. We know the topic string. We're going to send it in. And it may return, okay, topic's changed. Or it may return an error that you're not the owner. You can't do this. So this is a really, really simple permissions checking case. And if we look in the channel code itself, we'll check the topic function. Topic receives a PID and a message. It returns OK or error not owner, the same returns that we just saw, right? This is a call. It's returning a unique value, not just OK. So synchronous communication to change the topic. We're going to call doTopic, which of course is just like we always see. The one exception is topic 1, where we can just, the topic is the return value. So this one's like a little cheat, right? But topic 2, we got to actually do some state update stuff. So we're going to go down to topic 2. If the message, if the requester PID matches the owner PID, we're going to go to topic 2. If there is no owner, we're going to go to topic 2. So in this implementation, if there's no owner to a channel, anybody can set the topic. If you are the owner, you can set the topic. But if there is an owner and you're not that owner, you get the not owner response. So topic 2. Now that's, in a real system, that would be, of course, to prevent channels from becoming kind of like just floating out there and unmaintained. Any user could pick up the admin load. And in this one, you can be a pirate, right? You can go into any unknown channel and just claim it, which that's what doClaim does down here, right? You can only claim if there's no owner. In this case, with setting the topic, if you're the owner, if the requester is the owner, or if there is no owner, then you'll advance down to topic 2. Same thing as before, right? We're not writing all this in line because I don't want to write this junk twice. Because what if something about the way that topics work changes? I don't want to edit it twice, so that's why we've got topic 2 kind of clipped out. And you could have a single clause. You could do a conditional. If owner is requester PID or none, whatever. But just matching on it is less messy. Now the channel manager that's got the list of all the channels, all the channel names, right? That guy's also got, he maintains a list of all the topics too. That way, when you type list in the in your terminal, when you type in list, you get a list of the channel names and their topics, just like you would in an IRC client if you want to list all the channels in IRC. It's basically the same thing. But we don't want, every time a user issues a list command, we don't want the channel manager to spam all of the channel processes to get a hold of their current topic string. So instead of that, what happens is the owner of a channel tells the channel to update its topic. In the process of updating its topic, it forwards that topic to the channel manager. So the channel manager also gets a copy of it. But these are distinct, right? And of course, if the channel crashes or goes away for some reason, the channel manager is monitoring it. So the whole thing, the channel name, along with the channel and the PID, all that's just gone from the list at that point. So it cleans itself up in that way. So anyway, we're going to find the requester PID in the list of users. Now, note, we're doing key find, but we're not doing a case if he's a user. We're expecting that if this is a requester PID and if they called this topic function, then the caller should have already checked that he's part of the channel. Now, is there a potential for a race condition here? Yeah, technically there is. It'll probably never pop up, but in a human speed system, it's extraordinarily unlikely. But if this system were a little bit higher speed, we would probably do, instead of having the am I in this channel check just over there, we'd probably do it here also. We would match on the case where we do list key find and that user didn't exist in the users list. We're not handling that case here because it's not going to happen in the course of playing with this system. Now, remember, I mentioned that IO lists we could be using binaries or we could be using strings. Doesn't matter. I've set this up to use strings because it's nicer to read, and there is like zero performance impact, practically speaking, on how fast this is going to run using strings instead of binaries. For a chat system like this, if we were doing something much heavier with several gigs of text in memory at once, then we would probably switch to binaries. But it doesn't really matter. The way that we're doing the editing here, though, you notice I don't have username ++ set topic 2 +. I'm not concatenating anything. I'm just constructing a list. Username is a string. This is a string literal, which is also a list, right? So this is a list. This is a list. From here to here is a list that's got a list, a list, a list, and a list. And that's it. Now, why does that work? Because in Erlang, if we take a list whose members may be strings or other lists or lists of lists or lists of binaries, it doesn't matter. When we put it on the wire, when we put it on the socket, it flattens the whole thing out into a binary value to send across the wire. So we can defer that. We don't want to do extensive string processing if we can avoid it, right? Building a list is cheap. Traversing a list is more expensive. So we're not going to traverse anything. We're not going to concatenate anything because strings and lists are the same thing, same data type basically in Erlang. And all lists are Lisp-style linked lists. So traversing them, if they're very large, could be expensive. Again, in this case, all these strings are so short that you'd never feel it. You would never notice if I did just ++ all these together. But this is an idiom that you'll see a lot in Erlang, is just stacking a list up with elements, and some of them are binaries and some of them are deep lists of strings and some are strings, and you just send all that junk to the socket. Another thing you can do is call the Unicode functions that output lists, a flat string, or output a binary string as a UTF-8 value. That function does basically the same thing at the socket thing, or the file when you write to standard out, or if you write to a file, the same kind of process happens. So sometimes you want to make sure that you've got normalized UTF-8 values, and you can feed one of these lists like that to the Unicode module also to get back out a flat list that's normalized and is definitely legal UTF-8 values. Here we're doing all just like ASCII texts. There's nothing magic in these. So we're just packing them into a list and sending to the socket, and that's it. Notify is a function that has been defined separately here. It's called a bunch of places. It's not a very big function, but it's called a lot of places where you want to tell the whole channel about something that happened. And all that, this is another closure, same thing that we saw before, right? Build up a closure called notify. So we're going to notify the users. Notify gets the user PID, just like we did with the chat messages, right? Gets the user PID out. It calls the client notice instead of the client chat function. And for each, zips through that list and sends everybody a copy of whatever the message was. And that's it. There's really not much else to how this system works. I mean, it's just not, if you're leaving, I guess probably the only interesting thing I haven't talked about is leaving. When a user leaves the chat group, if there's nobody else in users, so key takes a value out of the list and returns the tuple value, the value that it got out, and then a new, like what the new version of the list is with that removed. If it's empty, this process just exits. He's done. That's why they disappear. If you have a single user in a channel, when the last user leaves and the channel disappears, that's why. Because this is happening. We're matching on nothing. We're matching on an empty list of users. There's no more users left. And we're exit normal. If we match on the, notice up here at do leave, we assign the owner PID value, and we match on if the PID is the same as the owner. If it is the owner PID, we're going to demonitor that user, and then we're going to give a specific message that the owner left, and we're going to update the state to where there's no owner. If it's anybody other than the owner, and we have users left in the channel, we're going to demonitor that user. They're removed from the users list, and that's it. One thing here actually that I can do, I just typed through this too fast. Demonitor flush, what that does is it takes any down message that may have happened, like while this is processing, over here at the same time, that client may have crashed. Then there's a down message over here waiting in the mailbox, and he's going to get it, and he'll be like, that's an unexpected message. That's weird. What demonitor flush does is it checks for a down message in the mailbox, and it removes it if there is one, so you don't have to handle it. It's just gone. And we'll see actually handle down is really similar to that function. Handle down, we don't have to remove the monitor because the monitor is already fired, right? It's gone. If a client crashed, it didn't leave, it just crashed or exited, we're going to get a down message, so we're going to call handle down, which we've done here, right? We're going to search for that user. We're going to search to check and see if that PID is from our users list. If it is, and that was the last user, we're exiting just like before. If it's the owner PID, we're going to do that same update as before. And if it's just any user, we're just going to move on with the new users list. If he's not in our user list, we're going to handle it as an unexpected message, because it is. Like, why are we getting this down message if I'm not monitoring that? Or if he's not one of my clients, then why am I monitoring this process? That's weird to get a down message like that. So we would want to log that. And I log unexpecteds as a warning, because you shouldn't have surprise messages in your system that are not from outside. And I notice here, actually, I should have done the, remember the notice function? If we look at the do leave thing, we're notifying everybody. When someone leaves the channel, we're notifying all the other channel users about that. In this case, I didn't actually do that. But it should be, like, to do this properly, we would have inside handle down. We would have the notice in here to say so-and-so left, the same way that we did otherwise. And we could have a unique message, like he's gone from the system completely, or he logged off, or whatever. We don't really care. So that's how all these are handled. There's a couple of other details in the system you can go through and read on your own. I wanted to give a once-over on kind of how a system like this works. And there's a couple other points that I'd like to address with this, but at this point in the video, we're done discussing the code details as implemented here. There's two other things I'd like to address with regard to messaging systems in general. One is that there are a lot of pub sub type systems or subsystems or Erlang application packages and so on that you can find out there already. And a lot of them work similar to this, some of them don't. But the reason I'm going to the trouble to explain how this type of thing works and the structure of it is that this code follows a regular pattern that emerges. If you do Erlang for a long time, a lot of people kind of discover this pattern, that having a manager that knows what's going on and represents a service at a high level is better than having a God process that would take your whole system down if he crashes. And it's also better than interrogating a supervisor to find out all of its children and sifting through that and trying to figure out what's going on. And who should be doing the sifting? What context is that happening in? Is it another child or what? That's having a manager clears up a lot of things, and it gives you an appropriate place to do things like list all the channels. Another approach to not having a manager is to have an ETS table somewhere. The problem with that is the same as having a God process. You wind up having to have a God process that just owns all the ETS tables, which is the same. It's the same single point of failure problem that you get if you don't have a manager for a service. Another issue is failing to think of the subsystems within your system as subsystems that are somewhat independent of one another. These processes here, we don't want them on a single giant supervisor. If there's two failures here and two failures here, we're over our limit, and everything's gonna go down, depending on how the limit's defined for the crash trigger to collapse everything. But if our clients die, the manager, like if let's just say all the clients die, or we have like several clients die at one time, they fault at the same time. Or channels, if several channels fault at the same time for some reason, and the supervisor says, "Woo, this isn't any good, I'm going to go down too," and he kills himself, the channel manager is independently updating its state based on the monitors it had. So it's fine. It doesn't need to restart. And if you have persistent, long-held state, like if you have rules about what user owns what channel, and we're going to keep a user registry or something like that, and that lives in the channel manager, or if we have a channel registry, rather, not user registry. If we have a channel registry and it's like semi-persistent, we don't have to kill it off just because all the channels died. This supervisor can restart, and the next time somebody wants to join a channel, they can go through the same process as before, but the clients are not interrupted. They didn't get disconnected, and they can still do global shouts to each other even if all the channels are dead. They'll just notice that they got booted out of the system. They got booted out of the channels they were in, and they can go, they can hop right back into them. because it's like less than an instant that the supervisor is going to start back up and be waiting to spawn new channel children. We wouldn't have that robustness if all of these were peers. If these were all peer processes and under one giant supervisor that owned everything, which we could do, right? We could get rid of this layer. If we got rid of TT clients and TT chans and just put everything straight under TT sup, which is an anti-pattern that I see a lot in, sometimes in production code. One thing breaks over here and the whole system goes down. Now, ideally, nothing breaks ever, right? And you don't write expecting to have bugs that are going to crash anything ever. But if you want to get robust behaviors out of Erlang, you have to structure the code in a way that allows the system to react in a robust way. And that means breaking up stateful concerns and making a conscious decision what kind of state, when we lose the state that's held in this process or owned by this process, is that a big enough deal to shut the whole system down and restart everything or not? And if you break things up by subservices, the answer to that question becomes very obvious very quickly. So structure is like super important. And that's part of the reason I'm showing this. The other reason is instead of just using pub sub systems that are pre-written, it's very common to have the case that you start out your system with a pub sub system and you use something that's like pre-made and you're like, man, this is cool. Okay, I got this started really fast. It only took me 20 minutes before I could show my boss something. Or 20 minutes could be 20 hours, doesn't matter. You feel like you're moving very quickly. Well, you wind up also, not always, but often, a pub sub system doesn't quite fit what you wanted to do. And I've seen this exact case with a trading system before where you had two players and they're supposed to trade. And the trading system itself, each trade is like a chat channel basically. And it's going to govern the decisions. It's going to guarantee that you've got transactional compliance from both sides before a trade can occur. Somebody started out writing that as a pub sub system. They're like, hey, well, it's just messages going between players, so pub sub will work, right? Well, no. There's a hacky way to make that work that's very hard to maintain and understand, and when requirements change later, it's super hard to edit and change because you're now married to this thing in the middle, all the code's written for, and arguing to the boss like, hey, we should remove that and write our own process-based trade decision system. It should be a process that understands what trades are, and that'll make all the inside of the program, the kind of protocol that's defined between these processes will all be straightened out, and we won't have to carry so much memoized state in on both sides of the trade. And then if it breaks down, we have to write more cleanup code and so on, and try to do that in a way that doesn't confuse players if we get stuck in a weird state on either end of the trade. You just need to write a custom process, and it's not that hard to do. It just feels slow because it's a couple of extra hours sometimes. But writing a custom process that understands the nature of what you're trying to accomplish, especially between processes, is a much different thing than just writing a pub sub system. And broadcasting messages is so trivial that there's not really... I mean, if you read the code in this module, you'll see it's not that hard to keep track of, kind of client processes or subscribed processes. It's not hard to clean them up when a down message comes in. It is not hard to broadcast to all of them. None of this is hard to do. And, in the case of the trading system, each different trade, every transaction that's going on concurrently is a different process. You don't make a single transactions process. You make a transactions service. And that would be a supervisor, just like here. TT chans, it would be TT transactions. And below that, we would have a transaction manager. You ask the manager, hey, we want to initiate a transaction, so we need somebody, a third process to manage that for us. One other tricky thing is if you have two processes that are identical, communicating directly, and there's any blocking calls in that communication, you have just created the opportunity to create a deadlock. That's how it happens. A and B send a message to each other, synchronous calls to each other at the same time, and they're both waiting for response, and you're just stuck. So if you have a third process, you can change that situation tremendously, because that third process takes these randomly occurring events and it provides, it creates order out of the chaos, the literal order. I mean, like timing order. It creates sequence out of chaotic message orders, and that is a very simple way to step around most deadlock situations that occur because of identical processes communicating in a synchronous way. So anyway, my point is, in writing concurrent systems like this, you'll run into a lot of cases like that. You'll think PubSub is a solution. It's a solution for everything, or process groups or process registries are a solution for everything. And it turns out that's not the case. If you put, like all the channel names, for example, when we join a channel, we're looking up a channel name, right? We could have a process registry that registers all process names, but we still have to have a channel manager. Like as a service, we still have to have a service level concept of what are channels, because there's a meta service, or there's metadata and meta states that apply to the service as a whole that's above the level of the individual channels themselves. So just having a channel PID is not really that useful to you. Something needs to be in charge of the life cycle of those channels. Something needs to be in charge or aware of meta or persistent state that applies to all channels, or that applies to all users or whatever. So having a manager is it's like just a natural spot to put that type of code and responsibility, and it keeps it all in a nice little package so that you don't have clients too intimate with channels and channels too intimate with clients and so on. And they can all these components can crash separately from one another. I wrote a blog post a while back called the service worker pattern. And that's my own term. It's not like official, but that in that one I showed diagrams that are kind of like this. They're just a little bit larger. There's more things going on. And if you look at that, it's an example of a game server where you have the world map management processes is one service, and the client connections is a service, and the mobs are a service, and the item management is a service. All these services work together, and there's also a chat lobby and so on, because you could have multiple games in a single server. So you may have a games lobby or whatever. You may have web interfaces. You may have an interface to like WoW Armory that plugs into a backend cache of the current WoW data. And a lot of that type of thing is common now, having a web interface over a real-time game or a game that's running through separate native clients. And you may have a text interface to it and so on. So multiple interfaces may exist to a single system. And each type of client handling, as I kind of discussed before, you separate the idea of user from client. Client connection, so a connection handler becomes separated from a user. And they could both be live processes. But those would be independent services from one another. The web interface is orthogonal to the idea of having a concept of users or clients in your system, and so on. So anyway, this pattern shows up all the time. ZX helps you template in that way, so it's a lot less work when you're going to write your own system like this. This took about 2 hours, and that's not a fair assessment of how much work is involved, because I've written systems like this a lot. So there's probably like a full day shortcut in that, just because I already kind of know what the pieces are, because I've written tons of chat systems and backends of various often game systems, but like business is getting big in that now too. So messaging systems I'm pretty familiar with. This wasn't that hard to write because I know the pieces. But if you write, the more various types of systems that you write, you'll see this as somewhat of a skeleton to a large number, not all, but a large number of different types of services that involve multiple users and multiple things happening concurrently will often fit into a pattern kind of like this. There's other patterns though that will emerge, but this is a pretty common one. So anyway, I'm gonna put this code on in a repository where you can get at it, and I'll probably comment a couple things up, or I'm on GitLab mostly, so that lets you put like comments all through the middle of code that you can like click and open and read them. So I'll see if I can do that. I may diagram some stuff out. I haven't decided. If anyone has questions, or if there's anything you'd like to see added to the repository, like, I could draw diagrams for the way things work, or detail the way that commands get translated to actual actions within the system. What are the steps? What are the message steps that get passed, and so on? If that type of thing would be helpful, please let me know. I really would like to see people kind of skip over this intermediate Erlang. It's like Erlang's so simple, the language, it's so easy to learn, and then you're just thrown in the deep end of the pool and like expected to write OTP applications that are structured in a robust way, and like you have no idea what's going on. And there's very little I wouldn't say there's no discussion of it, but there's little discussion of how to do that, and there's not a lot of materials out there right now that explain how that works, or what is a robust structure, what's a crash kernel, and so on. So every bit of new material going out into the world is good, and I hope folks enjoyed this. I hope that you learned something from it. I hope it gave you some food for thought at a minimum. If you're not an Erlanger and you're just looking at this for like, how would an Erlanger go about this? These type of instructions and patterns may apply to your own, the way that you do stuff in your language or environment or whatever. I think it's inevitable with the proliferation of cores on computers now that other languages are going to have to start adopting things like this, whether they're tack-in libraries or whatever. But these type of patterns are going to become very important to understand. And this is a simple one, but it pops up all the time. So anyway, thanks for sticking with me this far into the video. And just send me your questions if you've got anything, or if you've got improvements or recommendations, or if you've got anything you'd like to see. If you're curious about something that occurs in the Erlang world, let me know, and I may have time to do a video on it. So thanks a lot. Bye.